Okay, the purpose of this video is to go over a summary of the inference procedures that we've been talking about this entire inference unit. So there's been a lot of tests and intervals. Here they all are. So you can see that there's actually a total of 10 procedures. They're broken up into 5 categories. The names will usually tell you what they're doing. So the 1 or 2 part in the beginning tells you how many samples you have. So notice that there's 1 and 2 proportions and 1 and 2 sample. The sample stands for sample means. So I don't know why they don't just say means, but they don't. So be aware the next part of the name talks about whether you're doing proportions or you're doing means. So when you see the prop or proportion, it's proportion, and then sample stands for sample means. Realize the paired interval is also dealing with means. Then the end part first talks about the distribution you're using. Now, with these proportion procedures, we're able to just use a regular normal curve. So that's what the Z stands for, Z like in Z-score that you find on a regular normal curve. We discussed at length when you do means that if you don't have the population standard deviations, which you normally don't, and use the sample standard deviations, it distorts that normal curve a little bit and makes something called a T-curve. So these things have T in them. Now realize there is a version that also says Z. I doubt they'll ask about this, but the one that has Z in it is if you actually have the population standard deviations, then you don't use a normal curve. You just use a you don't use a T curve, use a normal curve. All right. But the vast majority of the time, you don't have that and you need the T curve. So that's why the T is there, symbolizing a T curve. And then they all end in, whether they're a test or an interval is how they end. So one of these is what you use, and I'll talk about basically each part of this, how you know what to use when. All right, so there's a total of 10 procedures. This is about, first off, how do you know what procedure to use when, and I mentioned I would talk more about doing these in a calculator. All right, so I'm going to focus on those two things. How do you know when to use one of these procedures based on the information you're given, and then how could you use technology to get you to the end? Basically, the calculator on an interval will calculate the confidence interval right for you. On a test, it won't go through all of the calculations, but it will give you the T-score or Z-score, and it'll give you the p-value, in which case you can then make a conclusion from that. All right? And over here it just says that the formulas, calculations, and conditions are all based on the procedure you're using. So attached with this in the folder where this is stored, you'll find that I actually have a document that, remember, they're allowing you to use open notes on the exam. I would use that document because the document basically outlines all of these things for each one of these procedures. So if you follow what I'm doing here, and you know how to pick a procedure, you can look up any of the calculations or conditions that you need. And then if it's able to be shortcutted with a calculator, hopefully you can do that. If not, at the very least, you can go through it by hand and get the parts you need or whatever you need to do. All right, so let's go through first, how do you pick these based on just reading a problem? So I went through the big 3 steps of how do you pick an inference method. So you're taking the exam, it's an inference question, you want to make sure you get the procedure right. So the first thing to do is to pick, are you doing a hypothesis test or making a confidence interval? Now, usually the context of the problem, this is one of the easier ones to pick as to what are you doing. Basically, you need to ask yourself one of these 2 questions, or ask them both, and which one does it fulfill. So in number 1, it says, you're going to ask yourself between, does it want a range for the true value? If it wants some range for the true value, you're going to make a confidence interval. Or are they asking you to determine if a particular value is true or false for the entire population? Basically, if you're seeing if some value applies to the population or not, that's a test. So you need to ask yourself this question if you want to know, are you making a confidence interval or are you making a test? Well, if they want a range for the true value, you need a confidence interval. If you just want to know if a certain value is supported in the population by a sample, well, then a test will do that. All right, so that will determine on this thing whether you do the interval or the test. I think that one's not that difficult to come up with usually from the context. Now, a little more difficult can be number 2. How do you know whether you're using proportions or means? Sometimes it's obvious, but other times there can be some gray areas, so I'll go over the gray area. Basically, the question you ask yourself is, are you dealing with categorical data? That is data that either is in a category or isn't in the category, so a success-fail kind of condition. In that case, you're usually dealing with proportions. Or is the data quantitative in nature, something that's somewhat continuous, or you have lots of data that has lots of different varying values, and they're asking for some kind of average or expected value overall? That would be means. So once again, you're asking yourself, is it categorical or is it quantitative? If it's categorical, it's going to be a proportions inference procedure. If it's quantitative, it's going to be a means inference procedure. And then the last one, which seems like it should be obvious, but I'll talk about how sometimes people get a little confused, is the one sample, two sample part. It's literally, you have to ask yourself, did they take a single sample or are there two samples? Basically, those 3 questions fill in all these parts and let you know which procedure to use. If you know how many samples you have, what kind of data it's working on, and what they want you to answer with the data, you can basically determine which one of these procedures is appropriate. All right, so let's look at each one in detail. The first one, intervals versus tests. So beware that both of these on the AP exam need the conditions checked unless they otherwise state it. Now, when they otherwise state it, sometimes they want to shorten a question and they don't want you going through the conditions check. If they don't want you to go through the conditions check, they'll state it in some way. But if they don't, if you don't see anything excusing you from checking the conditions, you need to check all of the necessary conditions, whether it's a confidence interval or a hypothesis test. Now, say you determine they want a confidence interval. The good news is the interval structure is always the same. They kind of give you this on the AP exam reference sheet. So the overall structure for every confidence interval is your estimate from your sample or samples. Typically, if it's a one sample estimate, or one proportion, you'll know what it is. They'll tell you in the problem. If it's a two sample or two proportion procedure, this will be the difference between them, difference between your samples. So you always need what's called that point estimate. So the point estimate is where you start building your confidence interval, and then you always add or subtract. So from that point estimate, you build outward. You build outward to the left and right, and then you calculate this. I put critical value because basically it depends on what curve you're working with. If you're working with a normal curve, it's a z-star, or a number of standard deviations on a normal curve. If it's a t-curve, then it's a t-score, or t-star, which will be how many standard deviations you have to go on a t-curve to cover whatever your desired level of confidence is. So this number, remember, is based on if you want to cover 95% or 99% or whatever it is. This is your z-star or t-star. And then the standard error, each procedure has its own standard error. That is on the formula sheet that I gave you. So if you need the standard error, it's based on the procedure you're using. You can look that up and calculate it. For proportions, it usually needs the P, the Q, and the N. For means, it normally needs the standard deviation for the original data, and it needs the N value. So those are all the intervals have this same structure to them. The test structures are also very similar. When you do a test, always make sure you're making a null and alternative hypothesis. The null hypothesis is always the normal state of affairs. So in a one sample or one proportion situation, the normal state of affairs is normally given to you in the problem. There's this is the way things are, or this is how we think things were, or it's whatever the unchanged or normal state would be. The alternative hypothesis would be contrary to the null hypothesis. Now, the null, if it's a two sample or two mean procedure, is 0, because we're always assuming there is no difference, all right? So you read the problem to get what the null hypothesis is, and then there's the alternative hypothesis. The alternative hypothesis is usually stating that that the true value is somehow different than the assumed null. Remember, with the alternative hypothesis, you can have it be two-sided or one-sided. Once you've made your hypotheses, you check conditions if necessary. But the major thing you need, which I'm going to show you how to get these in the calculator, is you're taking your sample value or values or difference, and you're going to test the sample value against the null. So the point of the test is you've made an assumption with the null. You want to see if your sample is consistent with the null, or if your sample is super rare and doesn't seem to support the null but supports the alternative. So what you do is you test your sample value on a normal or t-curve against the null, and you generate a z-score or a t-score. T-score, I guess that's silly. We don't need it twice. So you generate a z-score or t-score based on your sample compared to your null. Once you get a z-score or t-score, you use the resulting p-value. Remember, the p-value is the area that once you're at a certain z-score or t-score, it's all the area that's at that spot onward, either to the right or to the left, depending on where you are on the curve. So it's basically telling you how likely it is that you get a result like this or more extreme. So what you do is you use the resulting p-value, which is the area, to determine how likely this was to happen, and then which hypothesis does it support. Now remember that a high p-value means that your sample's likely to occur under the null hypothesis, which leads us to sort of going along with the null. So a low value here results in a high p-value, and a high p-value is consistent with the null. If we end up having a value that's really far away, our sample value is really far from our null, we'll have a very high z or t-score, and then that will create a low p-value. A low p-value means that if the null is true, it's very unlikely for this sample to happen. So a low p-value is inconsistent with the null. A low p-value supports the alternative hypothesis. All right, so the test structure is always the same. You make the hypotheses, you get a t-score, z-score, then use that, get a p-value, and the p-value tells you whether you go along with the null or you reject the null. Basically, remember, it's reject or fail to reject. We never actually accept the null. We just go, hey, we have no reason to dispute it. So the null is never accepted. We're never 100% positive. Remember, the null is either rejected or we just don't reject it. We don't have evidence against it. The second part, which is probably the most important part, is how to choose between proportions versus means. So proportions are always going to be a categorical question, basically how much of a population fits in a particular category. So I put, easy example, did you vote for Trump? Basically, it's a category. Either you voted for him or you didn't vote for him. So if someone asked this question, you would fall in one or two categories. Either you did or you didn't. Now, most students, if they're not old enough to vote, they couldn't vote anyway. But of people who could vote or whoever they ask, you do fall into one of two categories. So since it's categorical and there's a number that are a success and a number that are a failure, basically we'll consider voting for Trump to be success. This would be a proportions question. So we would use a proportions inference to answer questions involving something of this nature. Now, means, on the other hand, you want to check if the data is quantitative and roughly continuous. It can be totally continuous, but sometimes the data isn't perfectly continuous, like grades in school. If we're giving out averages, most time on the report card, they'll put 95 or 96. They will put 95.3. But so long as it's roughly continuous, like you have a scale from 0 to 100, it's not perfectly continuous, but it's got a lot of gradation to it. So long as the data is quantitative and seemingly close to continuous or truly continuous, this would be when you would want to use means, because once it's this kind of data, you're going to have a lot of different quantitative data kind of spread out, and we usually want to know about an average of that data. So we consider the average, and when we're considering the averages of two sets of data, those are their means, and we would use a means procedure. Now, typically, a giveaway is usually that there's some kind of percent or proportion, a fraction, in these situations. And in these situations, it's some kind of other number, like heights or weights. So that's one way to tell, but you do have to be careful. An example of means I had here was, what's an estimate of household income in JC? Well, household income is a continuous measure, and different people have different household incomes. And if we wanted to compare maybe JC to other municipalities, we might be interested in what is the average. If we sort of average it out, what's the average income in JC compared to different places? Maybe we could compare it to Beverly Hills and see how we do. But okay, so the one thing to be careful about, I did mention that percents normally point to proportions, but they can also be used for means. So this can be a little confusing. That's why you have to really decide if it's categorical data or quantitative data. So grades are a great example of how some questions with grades could be asked in terms of proportions, but other ones could be asked in terms of means. So even though grades are percents, it depends on whether the percent is actually a categorical question or the percent is being used in a continuous measurement sort of way. So the first example, if I used your grade to see how many people passed, well, say I want to know how many people passed the class, and you need 65 or more. So even though it's a 65 and whatever grade you get is a proportion, that doesn't make it necessarily a proportions question. What makes the first example something you would answer with proportions is because it's categorical data. It's either you passed or you didn't, and we could break that into different categories. So the percent we actually might get is maybe 90% of the students in the class passed the course. So if that's the case, that 90% is our proportion. So notice that this is asking a categorical question. Are you in the category that you passed or failed? And it doesn't really have to do with the percents on the grades. It has to do with the percent that fit that category. Now, the second question would be handled with means. Even though grades are percents and percents are proportions, and you'd think, oh, well, wouldn't I use proportions to answer the second part? Just because you see proportions like grades, which are percents, those percents can be averaged, right? So if I'm looking at everyone in a class, everyone has this continuous grade assigned to them. And since there's this continuous set of grades that are assigned to them, and there's a certain number of people, we could basically go, well, what's the average of this class? So despite the fact that we're using percents in the problem, the percents are being averaged they're being treated here as continuous quantitative data, where here they're being considered as categorical data. So if someone asks me the class average, like say I want to know, is the average of your class greater than the average of the class last year? Well, I'm basically looking to add them up, divide, and compare means. So just because you see percents or fractions or proportions, make sure you really answer the question as to whether they're categorical data or continuous quantitative data. That's really how you're going to be able to tell, because just seeing percents isn't enough, though it's usually a giveaway toward proportions. It's not always, all right? So beware of that. This can be a little tricky, but if you really ask that question and see the difference, you should be able to pick whether you're going to use proportions or means. The last thing is the one sample versus two samples. This shouldn't be difficult, but usually the problem occurs here with the one sample stuff. Because no matter what you're doing, you're working with two sets of numbers. In the one sample case, I say, well, there's literally only one sample taken. Now, when you do a one sample test or a one proportion test, the problem is that there's also some standard it was compared to. Sometimes people mistake the standard for a second sample. So don't do that. Don't confuse the standard for a second sample. You'll be able to tell from the problem if they took literally one sample and they're comparing it to a standard, or if they took two separate samples. All right. So you use one sample procedures when you see there was only one sample taken. There may be another number mentioned, but the sample is only from one group. Use the two sample procedures, obviously, when there are two different sampled values from two different groups. And in these cases where we have two different groups, like we sample from men and women, or we sample from kids and adults, or we sample from the poor and the rich, or whatever we do, we normally pick these two groups because we care about potential differences between these groups. If you have two samples, the goal of an interval is to give the range of the difference between these two groups in reality. So if we think, the rich are more educated than the poor, we could look at the number of years of education each one has and then see if there's a difference. If there is a difference, we could use that to find if there's actually a difference in the population. A test is used to see if there is evidence of a difference, period. So the intervals give us a range of possible difference. Tests just tell us, is there statistical evidence of a difference or not? We may look at poor and rich people and find out that even though there's a sample difference between their education years, it may not be indicative of an actual difference in the population. However, we may also find that their sample differences are so far apart that it does seem to support that there's a difference in the populations, all right? So with two samples, there will literally be two sampled groups, and they're talking about a difference between two sampled groups. Some things to remember when you're doing two sample procedures is if it's a two proportion test, and when I say two samples, I mean it could be two proportions as well in this case. So it's a little ambiguous, but realize the one sample, two sample here could also mean one proportion or two proportion. So two proportion tests need pooling. So the calculator can actually do the pooling for you. But if you need to answer questions by hand, make sure that you're aware from the video I did on that what pooling is. It's not needed for two proportion intervals, but it is needed from the logic of the two proportion test. So if you're not sure what this is, make sure you go back and review that. So two proportion tests need to be pooled. Two sample tests don't need pooling. The calculation can pool them, but it's not required. In fact, don't do it. Two sample mean procedures. Remember, if you're doing two sample mean procedures, the degrees of freedom is basically going to be determined for a T-curve using the calculator. If you remember the lesson I did, there was a funky formula. They don't require you to know that formula at all. They just want you to get it out of the calculator. So the calculator is required if you're doing a two sample mean procedure to get the correct degrees of freedom. The last sort of two sample procedure is the paired T procedure. Paired procedures, remember, are only used if the groups lack independence. All right. So now that we've talked about how you pick those different tests, so basically you're going to ask yourself, is it one or two samples? Am I dealing with categorical or quantitative data? And am I using an interval or a test? If you can answer those questions, you'll normally know what to do. Now, I wanted to go over the conditions because basically the conditions are the same for all of them, and they like to ask concepts about the conditions. So make sure you understand why the conditions that are set forth need to be met. So I'm just going to review that, and this is for all of them. So there are the four big conditions for all these procedures. The first condition is randomness. The reason for randomness, if anyone cares, is it helps to ensure that the sample is representative of the population. Inference on a sample is no good if the sample's biased or not representative of the population. So we usually do randomness because we learned earlier on in the course that that's the best way to ensure that you're representing the population. This is normally required, but just realize if for some reason the sample, it's believable that it is representative of the population for another reason, you don't actually need this if you know for some other reason that your sample is representative. one exception to the randomness thing is if you're doing an experiment. Sometimes experiments, well, you're not trying to generalize it to the population. You just want to generalize it to the group that you're experimenting on. So if you're just picking representative groups of your experiment, you may not necessarily have to randomize them, or they may have already been randomized through the experiment. So realize that the purpose of randomness is to make sure your samples represent the population. If that's the case, this inference stuff works, and you want to make sure that that's the case. So most of the time you need randomness. It's the rare case where if somehow you know the sample is representative for some other reason, it may be possible to skip the randomness in that case. All right. Independence was a big one. Basically, independence is required for the sampling, or basically it says required, or the sampling distributions won't come out normal or t-distributed. So independence is a requirement to get those sampling distributions to work, basically to get the normal curve or t-curve to appear when you're sampling over and over and over again. Basically, individual data points should be independent of each other. And group data, things should normally be independent across groups, with the exception of the paired procedures. The paired T procedures are purposely created to handle when the groups aren't independent. But even if you're not independent across groups, each pair still has to be independent. So independence is still required. And like I said, it's major reason, if anyone asks you or you're wondering, the reason independence is necessary is so those distributions form into those familiar shapes. If they don't form into these shapes, we can't do our procedures. The next procedure that's talked about as the 10% condition. The problem with the 10% condition comes from the problem of independence. If you take too large of a sample from a finite population, the trouble is when you take too many items, you start to lose independence. You've taken so many items out of the population, you start to change the probability that you might get a certain item. So if you take too large of a sample, the independence is no longer assured. If independence isn't assured, then we can't get normal and t-curves and stuff like that. So the main purpose of the 10% condition, if anyone asks, its major purpose is so you don't take a sample that's too large. And the reason you don't want to take a sample that's too large is you don't want to lose independence. Now, notice I said a finite population. If something can be done infinitely in theory, like flipping a coin, you're never going to run out of coin flips. So typically for infinite populations, you don't have to worry about the 10% condition, because basically you're never going to flip a coin 10% more than what is possible, because basically you can flip a coin to the end of time. So realize that the 10% condition deals with finite populations, not things that you in theory could do infinitely, like rolling a die or flipping a coin. All right. But if we're talking the U.S. population or the population in New York, you got to be careful you don't grab more than 10%. And then the last set of conditions, named differently depending on which inference it is, but basically they're referred to in general as the large enough conditions. The 10% said you don't want to take too many. Those large enough conditions say you don't want to take too few. Basically, if your samples are too small with proportions or with means, you haven't actually taken a large enough sample for that normal curve or t-curve to really lock in. So be careful to make sure that the samples are large enough. If it's proportions, you use the success-fail condition. You use n times p and n times q. If there's two samples, you do n times p and n times q for both. Basically, remember that with n times p and n times q, they need to be greater than 10. If that happens, this condition's met, and you have a large enough sample where a normal or t-curve will make a really good approximation of it. In the case of means, there was the nearly normal condition. It serves the same purpose. Basically, we want those t-curves to form. The ideal is having your n more than 40. Now, if the n wasn't more than 40, you could look at histograms and use it for lower numbers, but you had to be more careful with it. This is where I'll let you know that even though this is sort of the industry accepted standard, I've seen on AP exams that they're okay with the number 30. So on an AP exam, if the number's over 30, that's good enough for them. Now, I don't know why it's different from like the industry standard, or I don't know if maybe there's a disagreement about when this thing basically kicks in. But the purpose of having a large enough sample size is so the central limit theorem kicks in. The central limit theorem makes a roughly normally distributed sample distribution, which is required to do all this inference, all right? So make sure that your samples are large enough with proportions. It's n times p, n times q, success, fail. With means is making sure that these are large enough. I said on the AP exam, if it's over 30, you're good. If it's under 30, you just got to check the distribution of the original data, make sure it's roughly unimolar and symmetric. All right, so let's finish this by talking through a couple examples. I want to show the calculator and talk about how I know which procedure to use. All right, so that's what I'm going to focus on. So I'm not going to focus on actually doing these all out by hand like I did before. I'm basically going to go, which procedure is it? And then find the procedure in the calculator and show you how to use the calculator to get the major stuff that you need out of it. So if I read this example, it's about American women. We want to know if they're taller now than 100 years ago. So why might this be the case? Well, we have better nutrition now. We have a better disease control, though it's funny I'm mentioning this during the coronavirus outbreak. But in general, you know, people don't get measles, mumps, rubella. We got all these vaccines and stuff like that. And they'll probably eventually get a vaccine for coronavirus too. So basically, we have greater health now, and that may lead to people being taller. So that's the question. Are women taller now than 100 years ago in the United States? So we're given a standard. So they tell us the average woman was 5'2" in 1920. So that's not a sample, that's a fact. In fact, that's our standard. So we want to make sure that we understand that this is the standard we're going to go by. So since this isn't a sample itself, I'm not going to count it as if it were one. So when I go on, I have that standard of, in 1920, we just know for whatever reason women were 5'2". Now a sample's taken. So a sample's taken of 108 women this year, 100 years later, and they find that the women now have an average of 5 foot 3.6 inches. And this sample of 108 women comes out with a standard deviation of 2.7 inches. So basically, what should we conclude? So what procedure am I going to use? Well, to talk through this, I have one sample being compared to a standard. So this is one, and so this is going to be a one sample procedure. Is it means or proportions? Hopefully we realize, well, these are continuous measurements and they're not categorical data. So since these are continuous measurements and they're talking about the average of these measurements, we're going to use a means procedure. So it's going to be a one sample, whatever. What's the rest of it? Well, we need to determine whether we're going to use a test or an interval. Now, we might be able to get this information from both, but they just want to know, are women taller now? So is this standard still in effect, or is the standard not in effect? We can use a test to get this information. So I'm going to do a one sample t-test to see what we should conclude about this information. So basically, our null is going to be that women are still 5'2". Our alternative is going to be that women are taller on average than 5'2" in the population. So now to do this in the calculator, once you know what procedure you're going to use, you can go to tests. So you go to stat and move on over to tests. Now, unfortunately, the one sample tests don't say one sample on them. So you'll see number 1 says z-test and number 2 says t-test. T-test is telling me it's a one sample t-test. Why is there z-test? Well, z-test is for if you happen to have the population standard deviations, you wouldn't need the t-curve. You could use a normal curve with means. Like I said, we normally don't have that. We don't have that in this case. So I'm going to go down to number 2 and select t-test. When you do a test in the calculator, if it's means, you can always get a list of data to input in here, so you don't have to put all the stats. But I don't have the original list of data. I just have the stats. So what I did here is under stats, you need to put in under mu naught, right here, my finger is, mu naught is your null hypothesis. My null hypothesis is that women are 62 inches. So I can't really put in 5'2", so I'm going to convert to inches. So basically, if women are 5'2", they're going to be 62 inches. That's my null hypothesis. My sample came out that women were 63.6 inches. and the standard deviation of that sample is 2.6. The last thing you need is how many people are in the sample. Well, they asked 108 women, or measured 108 women. So put in the data that it asks for, and the bottom part lets you do one or two-sided tests. So sorry if it's a little blurry. I'm doing my best here. Under the mu, if it were a two-sided test, I would do the mu not equal to the null. If I want it to be one-sided, I can either make it less than null or greater than null. Now, I want to see if women today are actually taller than they were before. So I want to see if my sample means that the actual value is greater than the null value. Are women taller than 62? Once I have all this in, you can do one of two things. You can calculate or you can draw. I'll show both. Calculating is the big thing you want to do. If you calculate, it gives you the t-score. So basically our sample, if the null is true, our sample's 6.15 standard deviations away. That's hard to do if the null is true. It also gives me the p-value. The p-value is extremely low because remember, even though I have 6.55, that e to the negative 9 means 10 times, this number times 10 to the negative 9th. So this is a very, very, very tiny p-value. So basically from the calculator, I can make my determination. The p-value is really low. So since the p-value is really low, I'm going to reject the null hypothesis. So basically, I don't believe, or this sample provides evidence that women are no longer 5'2". So I'm going to go with the alternative hypothesis, was that women are taller than 5'2". Now, it doesn't tell me how tall women actually are in the population, but I know that this number is no longer, at least my sample seems to suggest pretty greatly that this is no longer the case. So our conclusion overall, are American women taller now than 100 years ago? This sample supports that, yes, women are now taller in the population. All right. If you want to see what calculation does, so let me get to that. Calculate will just draw a picture of the normal curve. Now, let me get this. Sorry, I'm trying to do two things at once here. Draw is what I mean to say. So draw will actually draw a picture of the t-curve or a normal curve, and it takes a little while, and it'll actually shade it in to show you the area. The problem on this one is the area is so tiny, it's not going to shade anything in. Remember, it's 6 standard deviations away, so it basically gives me the t-score and tells me the p-value is essentially 0. If the p-value were something larger, you'd see it shaded in. So you're not seeing anything shaded here. But notice that it can draw a picture for you as well. Also, one other thing, if you want to use that same data to create a confidence interval, if you've already entered some data in, like I have data into t-test, if I go down to, and I want a one sample interval, I can go down to t-interval, and it retains the same data. So say I want to make a confidence interval for the true value of how tall women are based on this sample. Well, it's got my mean already put in, 63.6, 2.7 standard deviation, and my sample size. Now you can set the confidence level because now I'm in t-interval instead of t-test. So since I'm in t-interval, if I want to make a 95% confidence interval or any confidence interval, just put in what confidence you want and calculate it. I'll leave it at 95%. And here's my 95% confidence interval. So I'm 95% confident the true mean of women in the population based on the sample is that in the population women are roughly 63 inches to about 64.1 inches tall. All right. And notice that this supports the finding of my test. If I'm confident the true value's in here, 62 isn't part of this, right? So 62 is outside this interval. It's very unlikely, this is the real value's in here with 95% confidence. That 62 is nowhere near here. So it supports the fact that 62 is probably not the real value. All right. So basically that's doing it in the calculator and how I determine which test to use. Let's look at 2 more examples and then try to make them go fast because this is getting long. So the second example says a poll in January found 242 out of 526 likely voters approved of the job Trump was doing. At the beginning of April, during coronavirus outbreak, I don't know why I made it two different words, but it's one word. But anyway, another poll now finds 306 out of 712 voters approve of his job. Now, from one poll to the other, it's a 3% drop. So now Trump might get this information and might want to know, well, does this mean my support has actually lowered, or is it natural variation? So basically, this is going to be a two sample procedure, but it's actually going to be two proportions. So let's talk about the fact we do have two samples. We have sample number one of a group from January, and then sample number two, which is a group from April. So we're sampling two different groups. So there's going to be a 2 at the front of our procedure. Now, even though I have two samples, it's actually proportions because it's categorical data. So basically, each time people were put into a category. It's not a continuous measurement. It's just a category. You either approved of Trump or you didn't. So in January, 242 people approved. And then in April, actually more people approved, 306, but it was out of a greater number asked. So it actually turns out the percentage went down. I think it's 46 to 43%, if I remember correctly. But overall, there's a drop of 3% in the samples. Trump wants to know, does this mean that he actually lost support? So this is going to be a 2 proportion. And once again, I'm going to test if it's actually lower. So this is going to be a 2 proportion Z test. All right. So if I want to do a 2 proportion Z test in the calculator, good news is this one's better labeled. All the proportion ones are labeled. So if I want to do a 2 proportion Z test, once I've identified that's what I'm going to do, I'll go down to 2 proportion Z test. And the important part is you need to put in not the proportions themselves, I should say not the percentages, but the actual numbers. So it's very important. Here's the data. It's very important that if they give you the percents, you need the counts. So notice that in my problem, I have 242 out of 526. But if they gave me 46% of people support him, I would have to find these numbers. So you can't put the percents in. You have to put in the counts, all right? So make sure that you do that, because if you put in percents, it's going to screw things up. So sometimes they give you the percents and you need to get the counts. Other times, like in this example, they just gave me the counts. So make sure the counts are in. Once the counts are in, once again, you can come down here and decide whether you want to do a one-sided or two-sided test. Since Trump wants to know if it got lower, I want to know if the original sample was greater than the second one, right? So I want to know if the population from January is actually greater than the population from April, and P2 is my April population. So once again, we can calculate this, or you can draw a curve. This one gives me a z-score of 1.06, so that's not that far away. It gives you a lot of other information too. It gives you the pooled value, and make sure that this is pooled. I'm not sure if I showed that part. Let me go back and show that. 2 proportion z-test. It must just automatically be doing it. Okay, sorry. I think it asks you for means, but it just automatically does it. I guess it ought to because it's supposed to. So this is the pooled number. So there's the January poll, 46%. There's the April poll, a little under 43. That's the pooled number. That's assuming they're no different. So now the z-score came out 1.06, so that's a kind of high p-value. So remember, under the null hypothesis, it would be that we would assume Trump didn't have a support change, that basically Trump support's the same as before. Under the assumption Trump's support's the same as before, what's the likelihood we see this difference? Well, it happens 14% of the time, which isn't that rare. So the good news for Trump is we're not going to reject the null hypothesis. The null hypothesis is that there's no difference. The alternative hypothesis would have been that April's lower than January and the support went down. So due to high p-value, we won't reject the null, and the null just says we don't have evidence that supports that Trump's support actually changed. So even though the April poll came out lower than January, we tend to think that that's probably from natural variation. If the population thinks the same of him, it's possible these two samples came out. All right. So once again, I decided it was a two proportion z-test, put in all the stuff, and they basically just gave me the p-value right there, right? So I can make my determination. Since this one actually has a sizable p-value, I'll show you the draw. So now it's going to draw a normal curve, and notice now that there's a significant p-value, it shows that p-value. So basically, this is the null hypothesis that there's no difference. This is how far different the sample is, and this is the probability of getting something that different or more extreme. It's actually not that unlikely. So that's why we seem to go, well, it's very possible to get this 3% difference based on the null hypothesis. So we don't question the null and go, well, it doesn't necessarily seem, there's no evidence that Trump's support dropped due to coronavirus, according to these polls. All right. Now, in real life, I think his numbers went up, and now they've sort of gone back down. So in real life, I made up these polls. So in real life, I don't know if this is the case. So don't quote me here. But overall, I do think for some reason he actually got a boost from it, and now I think his boost is kind of sinking away, and he might actually be lower than he was before. Who knows? Politics. That's why I'm not a politician. It's crazy having to pay attention to this stuff all the time. All right. The last one. Just to show you the differences, this one asks, do students who go off to college really gain the freshman 15? So if you've never heard of the freshman 15, basically they say once you leave high school, you get kind of fat. You leave high school and maybe you're a certain weight, or you're more trim or something, and then you go off to college and you come back and you've gained weight. So this is always jokingly called the freshman 15, or if someone's being really mean, they'll call it the freshman 50. But basically what I want to see is this a true phenomenon? Do you leave college, off to college, and do you gain weight? And once again, just because you gain weight, maybe it's, you're still developing. I don't know, you're 18, 19, you might still be getting a little more developed and a little heavy or something. So it may not be indicative that you're just getting fat, but basically, are you getting this extra weight from the time you leave high school to after your first year in college? So basically, you go from being a high school senior to a college freshman. Do you gain weight? So they pick a group of 47 college-bound seniors. They're weighed before they graduate high school, and then they're weighed again a year later. The difference of the individual weights. Now this, because they're befores and afters, so let's talk about the procedure. There are two groups being sampled, but be careful. They're not independent, because basically it's a before and after. So the after weights are obviously dependent on the before weights. Someone who's heavy before is going to probably be heavier after, and someone who's light before will also be heavier, but not probably to the magnitude of the person who was already heavy. So this breaks that independent groups thing. This is paired data. So if you can recognize paired data, well, then there aren't too many options. It's just either a paired t-test or a paired t-interval. We could do either or both. But basically, this is going to be a paired t-test just because I can tell from this before and after thing. So we don't have independent groups. That's what the paired t-test was designed for. So to do the paired t-test, remember, we can do this as a one sample procedure. So in the calculator, I'm showing this because it's not going to say paired t-test anywhere. You need to realize that paired tests are treated like one sample test. Even though there's two groups of data, they're paired up and treated as one sample. So they give me the information about the one sample. Remember, if they didn't do this, I'd have to find the differences between everybody, make a list and all that stuff. They did this already for me. They basically said the difference of the individual weights on average is 12 pounds. So what we found is, on average, people have gained 12 pounds. And the standard deviation of the individual weights is 18 pounds. So that's not the standard error, that's the standard deviation within the list. So even though people seem to have, on average, gained 12 pounds, within a standard deviation, some people have gained 30 pounds. Other people, if you go to the other end, have lost 6 pounds. So it doesn't mean everybody's gained weight. It just means on average there's a 12-pound gain. So with this information, so long as I have the mean of the difference list and the standard deviation of the difference list, I can treat this as a one sample procedure. So that's what I'm going to do. So I'm going to go to z-test. Now, it has my data from before, which I think some of it got zeroed out because I went into a different procedure. For this one, remember if you're doing paired, it's similar to a two-sample procedure in that our differences, our null is going to be that there is no difference between the pairs. So I'm going to leave the null hypothesis as 0. I'm going to give these people the benefit of the doubt and go, no, they didn't, they're not any heavier. Then what I can do, I went to z-test. I should have went into, I hate these videos. You make mistakes and it's too late to go back. Sorry. I should be in t-test. I accidentally went to z-test. I don't have the population standard deviation. So in t-test, I'm going to make the null hypothesis 0. I'm going to put in the mean difference, which was 12, the standard deviation of that list, which was 18, and the sample size, which was 47. All right, so there's all the data put in. Once again, I want to know if people are heavier, so it's still a one-sided test. Probably should have done two-sided tests because they're all one-sided in these examples, but whatever. So I'm going to keep doing the one-sided test. I want to see if the mean is now greater than 0. My null is going to be that 0. My alternative is going to be that it's actually greater. We'll calculate. And given the null hypothesis was 0, we're actually going to go with the alternative because the t-value came out pretty high. The p-value is actually quite low. So remember, a low p-value goes against the null. So the null was me giving them the benefit of the doubt. There were two groups. I gave them the benefit of the doubt and said, the two groups aren't really any different in weight. Well, this contradicts that. That sample of 12 pounds is extremely unlikely to come up if the null is true. So since the p-value is low, we'll reject the null and go with the alternative. It seems like there is some kind of freshman 15 phenomena going on, that the population of the students afterwards are on average heavier than they were before. So it's not just natural variation, it's legitimate, all right? If we wanted to do the confidence interval, just to see that as well, I keep hitting the wrong thing here. It's kind of like we're in class. If I want to make an interval out of this data, I just went to t-interval, and there's the same stats as before. Let's put it up. I'm going to change the confidence level. Let's do 99% confidence. So I'm going to make, since these guys are heavier, I want to see a 99% confidence interval for how much heavier a group on average you're expected to get if you go off to college. So let's calculate it. And there's a 99% confidence interval. So I'm 99% confident that when kids go off to college, on average, they gain anywhere from 5 to 19 pounds. So I don't know which number it is. No number is more likely than a number in there, but that's my confidence interval. So this also supports the fact that there is some kind of phenomenon. It may not be the freshman 15, but according to this confidence interval, it's at least the freshman 5, right? Because the true value could be anywhere from 5 to 19 based on this sample. 0 is not in this confidence interval, so that's why I can't go with the fact that that there is no difference, because the true value is not in here. All right, so this will be my last video for a while on any kind of new stuff, because from here on out, we're going to be doing AP review. So hopefully you really get all this down, because this exam is usually about 40% of this stuff. So hopefully this helps and you have a good handle on what these mean, how to pick them, and how to do them in a calculator. And like I said, if you want more details, you can go back and see the videos I've made, or you can look at that sheet that I provide that has all the formulas and conditions and all that stuff. All right. So this was a big summary of inference. Hopefully it helps you out, because I said this is a big topic, and it's really basically the culmination of everything we've done in the course. So if you think of from when we started till now, it was also we could do these kinds of procedures where it's kind of amazing that we can know a lot about a population from just taking samples of them. All right. And that's the big goal. If you want to know what was inference all about, it's basically using samples to know about a population and how we're able to do that, like why we're able to know how tall the average person is, or how many people support Trump and stuff like that. It's all statistics that allows us to know these things, because doing a census of a lot of this data is just not possible or feasible. All right. So with this, see if you can do the assignment. Hopefully you have a calculator. Once again, if you don't, send me a message. I'm trying my best for people who have asked to get them. The school is obviously going crazy with this stuff. So I'll try to get calculators out to people through the school as soon as I can. All right. Do the assignment, and then we'll move on to do an AP review. But this is all the content. So good luck.